Hello everyone. We continue with our this week's lecture. In the last lecture, we learned routing algorithm and which was Dijkstra's algorithm. In this lecture, we are going to discuss another algorithm, which is the Bellman-Ford algorithm. So the Bellman-Ford algorithm can be stated as it finds the shortest path from the given source node subjected to the constraint that the paths contain at most one link. So at most one link is contained in that path. Then it finds the shortest path with a constraint of paths at most two links. So first of all, it finds the shortest path from the source node with a constraint that there is at least one link. Then it finds the shortest path with a constraint of paths at most two links, and then so on. So this algorithm proceeds in stages, and this algorithm can be there are you can say notations which can be used. Now for the iteration of step 2, so this repeats. For the iteration of step 2 with h is equals to k, hop count is equals to number of nodes, and for each destination node n, the algorithm will compare the path from source to the node n. So this is how it proceeds in stages. So we have S is the source node, Wij is the link cost from node I to the node j, and if the two nodes are connected as usual, the link cost Wij will be greater than equal to 0, or it will be infinity if the two nodes are not connected. Then we have LHN, which is the cost of least cost path from the source node to the node n, under the constraint that no more than h links exist. Alright, so moving ahead. So step 1 is we initialize. Step 1 is the initialize. We initialize everything to infinity. So we initialize all the hop, all the nodes to infinity, and then in the step 2, for each successive hop we add, we compute the hops, and we try to compute the minimum distance from source nodes to the destination. And we continue with this step unless and until we explore more nodes or we explore the complete algorithm. So we are going to take the same example in this case. Now the same example we are going to do, but the same example we are going to consider over here. Let's understand how this algorithm does, how this algorithm works. Alright, so we have the same graph. We have the same graph. Now let's see how this works. So our step 1 is the initialization. As I told over here, initialization, we initialize all the paths to infinity, all the nodes to infinity for nodes not equal to the source node. If the node is not a source node, we initialize all the nodes to infinity, and we initialize hop count to 0 for all h. Right? So same thing we will have. First of all, we will make a table where h is the hop count. Hop count means number of links from source to the destination. So LH2, it defines the node and it defines the path. LH3 stands for node 3, LH4 stands for node 4, LH5 stands for node 5, LH6 stands for node 6. So we start with hop count is equals to 0, and in the hop count is equals to 0 for each node. If it is not a source node, we initialize it to infinity, and in the path we just put a dash mark. That means that we have just started. Initialization is done with putting everything with infinity and blank. Now hop count, we try to increase the hop count. I just understand the idea of the algorithm. The idea says we find the shortest path. First of all, we explore the graph starting at one link. Then we find the shortest path at most two links. Then and so on we carry on. So this is the purpose of the hop count. That means we are going to explore only one link now. So our source node is node 1. So we are going to find out the shortest path from node 1 to node 6. So our source node is node 1 and our destination node is node 6. Of course, this graph will give us the shortest path to other nodes also. Alright, now what happens in this, just understand it. Now hop count is 1. So what we do, let's go back to the graph. Now hop count is 1. Now that means we have h is equals to 1. We have started doing it. At this, we first of all we start with from node 1. From node 1, whatever nodes are reachable, we try to put the distance. From node 1, we can reach node 2 with a distance of 2. We can reach node 4 with a distance of 1, and we can reach node 3 with a distance of 5. Node 5 and 6 are not reachable. So as usual in LH2, that means node 2 can be reached at a cost of 2. Path is 1 to 2. Node 3 can be reached at a cost of 5. Path is 1-3, and node 4 can be reached at a cost of 1, and the path is 1-4. Node 5 and node 6, they are not directly connected to the source node. So again we put infinity and dash in the path. Now at this point we start exploring the other nodes. Now just remember, in case of Dijkastra, we try to explore each node individually at the step. But here multiple nodes or the same nodes can be explored at a particular time. So at the hop count 1, what data we have? We can reach node 2, we can reach node 3, we can reach node 4. So now we increase the hop count. So we increase the number of links. Hops means number of links. So when hop count is equals to 2, at this point node 4 says that I can reach node 3 at a cost of 3, right? So node 4 says that I can reach node at a cost of 3, and the algorithm knows that we can reach node 4 at a cost of 1. So the total cost of reaching node 3 via node 4 is 3 plus 1. So if I go back, now at this point node 4 says that I can reach node 3 at a cost of 3. And we already know that the cost of reaching node 4 is 1. So the total cost from to reach node 3 via path n1 to n4, n4 to n3 is 4. So what we do, we compare with our previous cost. At this time we have 5 previously. So now it's coming 4. That means it's the least cost. So what we do, we update it over here. And also the path, we update it to 143. That means the cost to reach or the path to reach to n3 is from n4 and the cost is 4. At the same time, node 4 also says that I am connected to, node 4 also says that I am connected to 5 and I can reach 5 at a cost of 1. And we already know that cost of reaching to n4 is 1. So we update the table that we can reach node n5, at a cost of 2 and the path is 1, 4 and 5. Now at the same time node 3 says that I can reach node 6 at a cost of 5, and we already know from the previous table. Now if you see over here, we already updated over here, but this updation will take place in the next step, because why we are putting 10 over here? By taking the previous cost into account. And we know that the cost of reaching node 3 is 5, and 5 says that I can reach node 6 at a cost of 5. So 5 plus 5 is 10 and the path is 1, 3 and 6. Now we increase the hop count. So we increase the hop count to see if there is further least cost and number of hops are increased. So 2 remains the same. Now if you see over here, if you see over here, node 5 says that I can reach node 3 at a cost of 1, and we know that the cost of reaching to node 5 is 2. So 2 plus 1 is 3, and we have the cost of reaching to node 3 is 4, and it was 143. But with increasing one hop more, the cost gets lowered. So what we will do? We will update our table and we will update the path 1, 4, 5 and 3. Similarly, now node 5 says that I can reach node 6 at a cost of 2. And we know that the cost of reaching node 5 is 2. So 2 plus 2 is 4. But we had cost of reaching node 6 from node 3, it was 10. So what we do? We update it and we make it 4, and we increase the change the path also, and the path becomes 1, 4, 5 and 6, because the path to reach node number 5 is 1, 4 and 5. So we update the path also. Next again, we increase the hop count to check whether we can find further low cost to reach the node 6 by increasing the number of hops. But we see that there is no such difference, because if you see over here, cost of reaching, for example, if I talk about from node 5 to node 3, it's 1, and from node 3 to node 6 is 5. So there is no such difference. So what we do? We put the last row as it is, because we don't have any further increase in the hop count which can decrease our cost. So the basic idea is we explore all the links simultaneously, and each link, and at each step we increase the number of links, we increase the number of hops to find whether the cost can be lowered or not. So our aim is to lower the cost, but the number of hops can be increased. So the cost of reaching node 6 is 4, and the path is 1, 4, 5 and 6. The cost of reaching node 5 is 2, and the path is 1, 4 and 5. Similarly, the cost of reaching node 4 is 1, and the path is 1-4. And the cost of reaching node 3 is 3, and this is the path. So if you can see, we did the same example, but in the Dijkstra's algorithm, we have so many number of steps. But over here, the number of steps have been reduced. So this is one of the advantage of the Bellman-Ford algorithm. So I have the same example over here. You need to solve this example by yourself by using the Bellman-Ford algorithm. And I have one more example. So the same example, now what you need to do in the demo, what I have done, I have taken node 1 as the source node. Now you need to take node 2 as the source node, and from node 2 find the path to all other nodes using the Bellman-Ford algorithm. And I have also added one more question over here. So the same algorithm same graph you need to take, and from node 2 you need to find the shortest path tree from node 2 to all other nodes using the Dijkstra's algorithm. I have explained you using the node 1, so you can do the same thing by taking the node 2. Similarly, we can apply the same algorithm to find the shortest distance from any node to any other node. Now the comparison. Calculation in Bellman-Ford, calculation for node n needs link cost. Now in this case, it needs to get data from the neighboring nodes also, plus the total cost to each neighbor. Each node in this case n1, n2, n3, each node will maintain its set of cost and the path for every other node, and they can exchange the information with the direct neighbors. Costs can be updated and paths can be updated based on the information received from the neighbors. Now in case of Dijkstra, each node needs a complete information on the topology. It must know the link cost of all the links, and it must exchange information with all the other nodes. So to sum up, I can say in case of Bellman-Ford algorithm, in step 2, The calculation for any particular node, it involves the knowledge of link cost to all the neighboring nodes of a particular node, plus it also requires the total cost, path cost to each of those neighboring nodes with a particular source node. So each node maintain a set of cost and associated paths. In step 2 of Bellman-Ford algorithm, based on the information from its neighbors, knowledge of its link cost and paths and the cost can be updated. Whereas in case of Dijkstra's algorithm, step 3 requires that each node should have complete topological information. So in this case, all the topological information must be exchanged with the other nodes. So to sum up, I can say that the relative merits of these two algorithms should consider the processing time, how much processing time is required for each of the algorithms and how much information needs to be exchanged or collected from the nodes. So the evaluation will depend upon the implementation approach and the specific implementation. Also, we must know that both the algorithms are known to converge under static conditions of topology and the link cost, and both of them will converge to the same solutions. But if the link cost changes over the time, the algorithm will attempt to catch up with these changes. So that's all about this chapter, and we have finished with all the algorithms in this chapter. So thank you so much.